DC circuits for MOSFETs. These are the things you need to remember when analyzing circuits with MOSFETs. First of all, the gate current is always 0, sort of like with op-amps. There is no current flowing into the gate, so whatever circuitry that goes around that, there is no current going into the gate. So we just automatically assume that that's not an issue. The drain current is always equal to the source current. So even though it doesn't look like it's the same current, remember there is a channel. It's exactly the same current that runs through the MOSFET, so those two currents are the same. However, the drain voltage does not equal the source voltage. There is a voltage drop between the drain and the source. So the voltage at the node that is the source and the voltage at the node that is the drain are not the same. They can be very, very close if the device is being used in certain situations, but most of the values that we use, some of them it will be in saturation and some of them it will be on the edge of saturation, but there will always be some kind of voltage between the drain and the source. We're going to assume that lambda equals 0 most of the time, unless I tell you that it's not. That also means that the output resistance is infinity. So those two things kind of go hand in hand. As far as overdrive voltage, sometimes it's very useful to solve for that. And for NMOS, it's VGS minus V threshold for the N device. And for PMOS, it's the magnitude of the overdrive times the source to gate voltage minus the magnitude of the threshold voltage. So in MOSFET circuits that use PMOS, the voltage are just a little different, and we use magnitude so we don't end up with a bunch of negative numbers. So, as I said, we are going to jump in and just do examples, and this time we will do a bunch of DC circuits that kind of all have different applications, and then on Wednesday we will do DC circuits that are specifically designed for amplifier circuits. So those are kind of different. So we'll look at those as a kind of a separate thing. So first example, we want to find the values of the drain and source resistances so that the transistor is operating with ID as 0.4 milliamps and the voltage at the drain is equal to 0.5 volts. So it's all marked here. And we have decided that the voltage at the top of the circuit is 2.5 volts and the voltage at the bottom of the circuit is negative 2.5 volts. So this is actually probably the simplest MOSFET DC circuit you can make. And it's totally impractical because it has two voltage sources and you would probably never actually do that. But for today, it's good. The parameters are given, so you've got the threshold voltage, the mobility times the capacitance is 100 microamps per volt squared, the length is 1 micrometer, the width is 32 micrometers, and lambda equals 0, just to make sure that you don't forget. So the easiest thing to start with is the value of RD, because we know the value of the voltage at the top, we know the value of the voltage at the bottom, and we know the current that's supposed to be going through there. So that will be the simplest thing to start with. And RD is just going to be VDD minus VD divided by ID. So we're just going to use Ohm's law to find that value. So that is easy. That one's done. And usually with MOSFET circuits, there'll be one that's really, really easy to find. And then there'll be one that's not as easy to find. And that's the case here, that there's a little more solving to go into the other resistor. So in order to find the value of RS, we actually need the value of the source resistance. Because that's what we're trying to find. We need to find the source voltage at the top there, at the source. And in order to find that, we need VGS. In order to find that, we need the overdrive voltage. So this is where in MOSFETs, you'll have to kind of think ahead and think, what do I need to find this value, and then kind of backtrack and figure out how to get there. So that's what makes MOSFETs a little more tricky than some other types of circuits. So the overdrive voltage, we've done this before, is the square root of ID times 2L over Kn prime W, and that's just taking the ID equation and flipping it around, which we've done before. And we know all of those values already. They've all been given to us, so we just kind of plug them in, and we get half a volt for the overdrive voltage. And also, just so that you know, I know that you know this, but I will just reiterate it. My general approach to writing down numbers is usually to use a prefix rather than a times 10 to the whatever, just because it takes up less space. So I use 0.4 M means 0.4 milli, and 100 micro equals 100 times 10 to the minus 6, which I know you guys know that, but I'm basically just using up time while y'all write. So we can find VGS because that's the overdrive voltage plus the threshold voltage. So we just add the threshold voltage to the value of the overdrive voltage, and we get 1.2 volts. And then we can find VS because VS is the voltage at the gate minus VGS. So when we do that, we get minus 1.2 volts. Now that we've got that number, RS is just VS minus VSS over IS, and IS is the same as ID, so we actually know those values. And the biggest thing is to pay attention to all the signs because everything's weirdly negative. So we have negative 1.2 minus negative 2.5 over 0.4 milli, and we get 3.25 kiloohms. And then if you had time and wanted to, you could go and put the values of RD and RS into the circuit, and then you could solve for ID and make sure that the value is correct. Most people don't want to take the time to do that, but you could, and then you would know if you were correct or not. So that's probably about as simple as these circuits can be made. Generally, they're not this simple because using more than one voltage source isn't practical, and this particular circuit doesn't have a great deal of use as it is, but it gives you the idea of the process to go through. So the next thing we're going to look at is something called a diode-connected NMOS. And as you'll notice, this is one of these circuits where everything's kind of the same. We have a value for, we sometimes use Kn without the prime, and that just means Kn prime times W over L, so it just takes all of those constants and kind of bumps it together. And we want to take this circuit and come up with a relationship with the parameters and the voltage and current. So basically, there are no resistors in this circuit. We have some type of drain voltage and some kind of source voltage, but we're really not worried about that so much either. And we want to just find the relationship between the two. So we have the regular ID equation equals Kn prime over 2 W over L, which that's all just Kn over 2. And then in this circuit, VDS and VGS are going to be the same value. They're going to be the same value because the gate is connected back to the drain without any resistors. So the gate to source voltage and the drain to source voltage will be the same. So we just basically plug in I equals ID and V equals VGS, and we get a relationship between the two. So why is this called a diode-connected NMOS when there aren't any diodes? Well, basically because we can take this circuit and we can actually provide a diode-like voltage with that, but it's adjustable. It can actually be adjusted depending on the value of the current, as long as the current doesn't change too much. So that being said, we will go look at a more practical example of a diode-connected circuit. and look at an actual design of one and see how we would find the values for that. So we want to find the resistor value, RD, that will set the drain voltage to 0.7 volts. So it will basically appear in the circuit kind of like a diode, like the forward drop would be 0.7 volts in this circuit. So we have parameters. The threshold voltage is 0.5 volts. We have the mobility times the capacitance is 400 microamps per volt squared, and W over L is 0.72 micrometers over 0.18 micrometers, and lambda is 0, just to make sure that you remember that. And in this circuit, VGS, VDS, VD are all the same, and they all equal 0.7. So this particular circuit has 3 voltages that are all the same because of how it's wired. So we can use the diode equation to figure out what current we would have. If we figure out the current, then we can figure out the resistor value, because we know the voltage at the top is 1.8 volts. We know the voltage below RD is supposed to be 0.7. So all we need to do is find the diode current, and then we can solve for the resistor value. So in this case, we just use the ID equation and just plug numbers in. So it's not even, we don't even have to think about it too much. And we plug numbers in and get 32 microamps for the current. Now that we know that, all we have to do is use Ohm's law and take 1.8 volts times the voltage of the diode, which is 0.7, divide by the diode current, or the drain current, which is 32 microamps, and we get 34.4 kilo ohms. I'll just let you get settled there. The nice things about recordings, I can cut all this stuff out. So I can stand here and talk, and then later on go out and just delete it.
Much appreciated.
Yeah, no problem, no problem. We only have one more example to do anyway.
Great.
Yeah. Ooh. You never know. All right, last example, and this is a little more complicated than the other ones as such. Is it? No, this one's not so bad. The next one is, the last one is a little more. Your phone just does not want to be quiet, does it? Oh, it's okay. Sometimes in the middle of the night I wake up and I can't sleep, and I'll just sit there and scroll through the news, and I'll mistakenly hit on something that's a video, and it'll all of a sudden start playing. And when that happens, my husband will wake up, and I'll hide my phone under the pillow and pretend I'm asleep. So he'll be like, "What woke me up?" Well, I don't know. Leave me alone.
Welcome to the life. Yeah.
I just want to think your house is haunted or something.
You know, he doesn't remember things half the time, so. We're all like that, those of us in our generation. Yeah, we're all kind of vague and like, yeah, whatever, okay. So, first thing, current mirrors. A current mirror is basically a circuit in which you add a second transistor and you get the same current in the other transistor, but you can also put it at a certain operation level if you wish. So we're going to find the value of RD2 that results in the other transistor operating right at the edge of saturation. So again, we have a lot of values that equal each other. VGS1 and VGS2 are going to be the same because there is a wire connecting the drain to the gate, and the gate is connected in both places. So that means that VGS2 and VGS1 are both 0.7 volts. And the current in the other transistor is the same as the original transistor, so we already know that that current's going to have to be 32 microamps. So all we need to do is figure out what the saturation voltage would be. And remember that point at which saturation occurs is when the drain to source voltage is exactly equal to the overdrive voltage. So that value is equal to VGS minus threshold value. We have both those values. So all we do is take 0.7 minus 0.5, we get 0.2 volts. So that's the edge of saturation value of voltage. And once we have that, we have enough voltages and current to use Ohm's law and figure out RD2. We know that at the top of it is 1.8 volts, at the bottom of it is 0.2, and then we're dividing by the current, which is 32 microamps, and we get 50 kiloohms. Yes?
Could you explain again why you have that second transistor in there? And why would you do that?
Because you are creating a circuit in which the current on the other side is exactly the same, and there are situations where you would want that. So it's a standard circuit called a current mirror, and it actually does have sort of that purpose, is to have the current in both of them to be the same. The last circuit that I'm going to cover is a CMOS circuit. We covered CMOS for about a minute to just basically say that it's an NMOS and a PMOS put together, and they have certain characteristics. And the lab that you do after next week's lab, no lab this week, next week is MOSFET characteristics, and the one after that is a CMOS LT Spice lab. So you get some experience without actually having a CMOS. So we have two transistors put together. Remember that with a PMOS, the drain and the source are flipped over, so I didn't actually mark them. Sometimes I do, but I can, I think. The gate obviously is the same in both areas, and then we have the drain and the source, and then this is the drain and this is the source with this one. So it gets flipped over because it's a PMOS. So we want to find the current in each one of them and the output voltage for three different values of input. Input is basically going to be what the gate voltage is. Yes?
Is the arrow not what that signifies the source?
Say that again?
Where there's the arrow on the MOSFET, is that what signifies the source?
I'm confused.
See the arrows coming into.
Oh, yeah, that's basically just the direction of the current flow. So, and if you look at it, you can see the current kind of goes down, through, and all the way to the bottom. But yeah, the current in a PMOS goes the opposite direction. We've also flipped it over, so it ends up going the same way. So we want three different voltages that we're going to look at, and three different values that's going to give us what we want. So there's going to be a table. Basically, we're just going to fill in as we go. And in the first case, we're going to set VG to 0. So we're just going to, yeah, see, I did actually label them on this page. Good for me. So we know that VGS for the PMOS is going to be that difference, 2.5 minus 0, so we get 2.5 volts there. And we always do like VSG for the PMOS, we just turn that around. So we know that value is going to be 2.5 volts, and it's actually going to be the same for the NMOS because the NMOS has a negative voltage at the bottom of it, so we have 0 minus negative 2.5. So basically both of those values are equal. VSG and VGS are going to be the same. And that means that the drain current for both is going to be the same, which is kind of obvious because they're connected together. It doesn't have to be that way, but it is that way for that particular voltage. So the two values are the same because VGS is the same, and we can calculate the drain current for either one or both by just using the Kn over 2. Remember, we lumped that all together into one parameter for this particular problem. And we just take VGS minus the threshold voltage squared. And remember, the threshold voltage for each one is going to be the same. And we're going to basically end up with the value that the drain current in the PMOS and the drain current in the NMOS is the same, which means there's no actual current in the 10 kilo ohm resistor because there is no current left over to go that way. So in this case, there is no current going this way, which means there is no current here, which means that V out is just going to equal 0 in this case, because if there's no voltage drop across the 10 kilo ohm resistor, it's shorted to ground. And so we get V out equals 0. So V in equals 0, V out equals 0. That's what happens in this particular case. Not the most interesting, but it is 1. So basically, we take one voltage in the middle, and then we're going to go to either extreme. And we're just going to go to 2.5 volts and then negative 2.5 volts and put those in and see what happens. So I did figure out the current. I just didn't say what it was. But so the next case we're going to do is Vn is plus 2.5 volts. And when we put plus 2.5 volts there, the voltage at the top of the PMOS is the same as the gate voltage. Because that's the same voltage, that transistor is off because it has no difference between the source voltage and the gate voltage, so it can't turn on. And that means that its current is 0. And this basically means that the other transistor is going to end up being in the triode region. Why do we know this? Because the gate voltage is 2.5 volts, and the drain has to be between negative 2.5 and 0. There is no other option. So the threshold voltage is a volt, and the gate to drain voltage then has to be greater than that. So because it's greater than that, it's actually in the other region of operation. It's not in the saturation region. It's actually in the triode region when it operates. So the circuit ends up looking like that. It ends up looking like just an NMOS circuit by itself. And now that we know that, it's a little bit easier to figure out what all the values are. Not quite as easy, but a little bit easier. So first of all, we know that VGS is 2.5 minus negative 2.5. So that's the voltage difference. We get 5 volts for VGS. And the drain current, we're going to use an approximation just to make it a little easier. But remember, in the triode region, the drain current depends on VDS as well as VGS. So it actually has a dependency there. So the drain current is approximately equal to Kn over 2 times VGS minus the threshold times whatever VDS is, which we don't actually know what it is. So we can get a relationship, but we don't have anything we can do with that. We do know that VDS is V out minus negative 2.5. We know that basically because VDS would be right here, and we just have to make a loop to make that equal to 0. So we know that V out plus 5 is going to have to be for VDS, whatever that happens to be. So with that in mind, we can create an equation. We can actually take VDS and replace that with V out plus 5. And we get this equation. And basically, we need a second equation. We can't just do this with one. So the second one, we're going to actually figure out what the current in the 10 kilo ohm resistor is, because that current is actually the drain current going the other way. The drain current's going down, it's going across, so it's going up through that resistor. So we can use Ohm's law and get a relationship where we take 0 minus V out over 10K, and that will also give us whatever the drain current is. Two equations, two unknowns. You go through and solve them in whatever way you wish to do, and you get that the drain current is 0.244 milliamps and V out is minus 2.44 volts, which is good because it's supposed to be between 0 and negative 2.5. This is why this course relies so heavily on circuit analysis. The good news is, now that we've figured out these values, the other circuit and the other voltage is going to be pretty much exactly the same. Because when we set the gate voltage to negative 2.5, we have the same voltage between these two. So that means Qn is going to be off. So the only thing that's going to happen is the polarities are going to be reversed, but we're actually going to end up with exactly the same current here that we had before, which means that we can take IDP and make it equal to IDN in the previous problem, and V out is just going to equal negative V out from the previous problem, and that is how we solve that.